Good morning, this is your stats sensei, Mr. Spensei, and we're going to party like it's 1999 and look at a regression equation question from 1999 that we've modified. It was not originally this long, but we're going to add several parts to it to make sure we cover everything they could be asking about it. So the prompt is, Liddy and Bob were searching the internet to find information on air travel in the United States. They found data on the number of commercial aircraft flying in the United States during the years 1990 to 1998. The dates were recorded as the years since 1990. So this would be 1990, 91, 92, 93, 94, 95, 96, 97, 98. Thus, the year 1990 was recorded as year 0. They fit a least squares regression line to the data, and the graph of the residuals and part of the computer output for the regression are given below. So here's the computer printout, and here's the graph of the residuals, okay? And we notice our residuals are random and without pattern, and that's good. And then we also look here and we go pretty high R squared. So this would be a pretty high R squared here. We also sit there and go huge T value, so a P value of almost 0, that's good because it looks like we're going to be rejecting. And so the question is it a line appropriate model for the use of this data? What information tells you this? Well, my students are always inclined, and be careful, don't fall into this. They say, hey, small P value, that's a good thing. That's why. R squared, pretty big R squared, that's good. Or they'll go calculate the R and they go 0.793 raised to the half power. And they go, wow, 89%. That is a pretty strong, that is a strong linear correlation. A line would be appropriate. No, those are all good things. We like those to happen. But the reason we know that a linear model is appropriate is because the residual plot is random and without pattern. A linear model appears to be appropriate because the residual plot appears to be random without pattern. Use the computer output above to determine the equation of the least squares regression line. So I can write this one of a couple ways, and basically y equals, there's my y-intercept, and this is my slope. So 2 y hat. Make sure you always put the hat on it, even though I didn't say it just then. You've got to include the hat. If you don't, you're going to get at best partial credit, possibly no credit. So please make sure you do that. So y hat equals 2939.93 plus 233.517x. And there's nothing wrong with that, except if I do that, I have to identify the variables. Y is the number of commercial aircraft flying, X is the year since 1990. So I could just sit there and go flights with a hat on it equals 2939.93 plus 233.517 years, in which case I've defined the variables inside of the equation. All right, what is the value of the slope? Well, this is a slope right here, all right? And this also tells me that years is my X value. And I always recommend writing the slope as a fraction first. So 233.517 flights over year. So for every one increase in the number of years, there's 233.517 increase in the number of flights. Or there's 233.517 more flights for every 1 year increase. All right, real important. And I just think it really helps to go ahead and write the fraction. The next is, what is the value of the intercept of the least square regression line interpreted in the context of the situation? Well, our y-intercept is 2939.93. And what it says is, in the year 0, which was 1990, our model predicts, that's not the actual number of flights, so hopefully there's not a partial flight. And if there was, I sure hope I'm not on it because things obviously went wrong. So our model predicts that there were 2,939.93 aircraft flying. Okay, so that would be year 0. All right, continuing with the same problem, what is the predicted number of aircraft flying in 1992? Well, 1992 is year 2, and so all I need to do is plug in a 2 into the equation, and I end up getting 3,406.96. Based on our model, we predict that there were 3,407 aircraft flying, okay? You can't have a partial aircraft, so this is where you're probably going to want to round. What was the actual number of aircraft flying in 1992? Well, they didn't give us that value, but they did give us the residuals. And what we know is for 1992, the residual happens to be 40. And remember, observed minus expected, or actual minus expected. So 40 equals the observed minus what we predicted. And up here we predicted 3407. So 40 minus the observed, 40 equals the observed minus 3407. So we would have expected by algebra, so what actually flew, not what we expected, actually flew was 3,447. Because 3,447 minus this value gives me my residual, okay? The next thing, write the coefficient of determination and explain its meaning and context. Well, our coefficient of determination is 79.3. So 79.3% of the variation in the changes in the number of commercial aircraft can be explained by changes in the number of years 690. All right. Basically, we're saying that it's a pretty good predictor, the number of for the amount of change. So it appears that the amount of variation really does vary by year, or 79.3% is explained by that. That means 21% are explained by other factors, but 79% can be explained by time. Right, the correlation. Well, as we did earlier, the correlation is just the square root of that, but I also have to check the sign of the coefficient. So in this case, 0.793 raised to the half power, 0.8905. So my correlation coefficient is 0.895, and my slope is positive, so my correlation is positive. All right. And since it's greater than 0.5, we have a strong positive linear relationship. Very, very, very important that you include these 3 words. You got to include the strength, you have to include the direction, and you have to say that it's linear. And then it's between what? X and Y, which is the number of years and the number of commercial planes flying. The next thing they said was calculate and explain what S is in the context of this problem. So calculate and explain what S is in the context of this problem. Well, S has actually already been calculated for us, but I want to remind you on how to do that. So what you do is you take this value and you'll divide it by, oh, I'm sorry, we don't even have the information. So we can't calculate it. We're just going to have to use the value that they gave us, which is 33.43. So 33.43, S is the standard deviation of the residuals. So 33.43 is the standard deviation of the residuals and measures the amount of variation, the number of commercial aircraft flying in a given year. All right. Key phrase is standard deviation of the residuals and measures the amount of variation in the number of Y for a given amount of X, or in this case, a given year. Identify and define the standard error. Well, standard error of the coefficient will always be on the slope row. So we're looking on the slope row, and here it says standard error of the coefficient. Now, sometimes they'll say standard deviation of the coefficient, or SD, or sometimes they'll just label it SE, but you need to know, look at the slope row, and wherever SE or STD is, that's going to be our standard error. Well, our standard error in this case is 4.316. And Because the slope is estimated from the sample, other samples are likely to have different slopes. The standard error of the slope quantifies the amount of variation in sample slopes that can be expected from different samples. So let's just say that we came up with a prediction line that looked like this. So there's our y-hat line. Well, someone else could take from the same population, take a sample and end up with a slightly different slope. Someone else could take another one and end up with a different slope. And because we end up all those different slopes, we have some variation or some error. And the standard error of the coefficient basically tells you how much variation you could expect from one slope to the next. All right, this is your Stat Sensei. I appreciate you watching and hope to see you on the next one.